So today we want to talk about right triangle trigonometry, and we've already been introduced to it a little bit we were introduced or maybe refreshed on 3 of the trigonometric functions. We've seen that sine of theta is equal to the opposite over the hypotenuse. We've seen that cosine of theta is equal to adjacent over hypotenuse, and that the tangent of theta is equal to the opposite over the adjacent. Now again, this is only true when we're dealing with right triangles. But along with those 3 trigonometric functions, we have 3 others that maybe we are not as familiar with. And those 3 are the reciprocals of the first 3. So you'll notice here that with the cosecant, if I have a cosecant of theta, that is the same as the reciprocal of sine of theta. So 1 over sine theta. Which means that if sine of theta is the opposite over the hypotenuse, then cosecant in a right triangle is going to be the hypotenuse over the opposite. And that works for all 3 of these. Our secant of theta is simply the reciprocal of cosine. And so our adjacent over hypotenuse here becomes hypotenuse over adjacent here. And for our tangent, we take the reciprocal of the tangent function, we get the cotangent function. So instead of being the opposite over the adjacent, we now have the adjacent over the opposite. Okay, and these are sometimes called the reciprocal functions of each other. And if I can take 1 over sine here and say that's cosecant, then I can also take 1 over cosecant and say that that's sine. Okay, it works both ways. And so these are actually called reciprocal identities sometimes. And an identity is simply a mathematical statement that is true for all values of the variable. Okay, so that means no matter what we put in for theta, these statements are always true. The sine of theta is always the same as the reciprocal of cosecant. The secant of theta is always going to be the reciprocal of cosine, no matter what we use for our angle measure of theta. A couple more identities that are going to be helpful to us as we move forward. One is called the quotient identities. One set is called the quotient identities. This is the identity that says that another way to think of tangent of theta is to think of it as the sine of theta over the cosine of theta. Now we're going to see in a couple of places throughout this chapter why that is true and why that makes sense. But one way we can show you that that would work is to again think in terms of those ratios from our right triangle. So we know that sine of theta is supposed to be the opposite over the hypotenuse, and cosine of theta is supposed to be adjacent over hypotenuse. Or if we have the one over the other, that's actually like dividing. So instead of dividing, I'm going to change that into multiplying by the reciprocal. And when I do that, you can see that my hypotenuses are going to cancel out. And so what I end up with here is the opposite over the adjacent, which we already know is the ratio for tangent. So this is just sort of proving the point that this really would work and that this is a legitimate identity and a legitimate way to think of tangent of theta. Similarly, we can do the same with cotangent of theta, again using the idea that cotangent is simply a reciprocal of tangent. We can say that cotangent of theta would be equal to the cosine of theta over the sine of theta. And these can be helpful sometimes because there are times where we have expressions that maybe have a tangent in them, where if we can rewrite it as sine over cosine, then we can simplify, or it'll be easier to work out whatever we're trying to work out. We have another set of identities called the Pythagorean identities. And the main Pythagorean identity says that sine squared theta plus cosine squared theta equals 1. Now the first thing we need to realize is we have a little bit of a difference in notation here. When we write sine squared theta, what we mean is that we're taking the sine of theta and we're squaring the whole thing. But they changed the notation on this and they put the square here rather than out here, because if you don't put the parentheses in this form, then it gets confusing as to whether we're supposed to be squaring just the theta or whether we're squaring the entire sine of theta. So in order to avoid the confusion, general convention is to put our exponent here in between the sine and the theta, and then we know we're supposed to be squaring the entire thing. Okay? Now, the sine squared theta plus cosine squared theta equals 1. That is the main Pythagorean identity. But there are a lot of different forms that we can get from that that are also part of the Pythagorean identity set. One thing we can do is simply rearrange things by moving terms to the other side. So we can rewrite sine squared plus cosine squared equals 1 as cosine squared theta equals 1 minus sine squared theta, just subtracting sine squared theta from both sides. We can do the same and get sine squared theta by itself by subtracting the cosine squared theta from both sides. Again, that can be helpful to us if we're trying to simplify things or trying to work with a certain problem where I've got this sine squared in it, but if I could make it into cosines, it would work better. And so this just gives us some options on how we can maybe substitute one equation in for another one. Okay? We can also modify our Pythagorean identity by dividing everything by the same denominator. So let's say we divide everything by a sine squared theta. So all three terms here get divided by sine squared theta. Okay, well what happens then is that this becomes 1. This cosine squared over sine squared becomes cotangent squared using our quotient identity from up here. And then 1 over sine squared becomes cosecant squared of x. And so this becomes another form of the Pythagorean identity that can be used with other trig functions in it. 1 plus cosine squared equals cosecant squared. And we can do the same thing if we divide everything by cosine squared. Take all three terms, divide by cosine squared theta. Now we've got sine squared over cosine squared, which will be tangent squared, using our tangent quotient identity. Cosine squared over cosine squared is 1, and 1 over cosine squared will now be secant squared. And so this gives us another possible form of the Pythagorean identity that we can use if we need to change things around a little bit to make our problem easier to work with. So these are just some different identities to keep in mind as we go forward. You'll see them pop up here and there. They'll be useful to accomplish different things, and we just need to know that these are legal substitutions that we can make to help things out. How we doing? All right. So all of these versions are Pythagorean, and that leads us then to our special angles. So, if you remember from geometry, we have special triangles, and one of the special triangles is the 45, 45, 90 right triangle. If we use this right triangle, we can see that it is a triangle that has two equivalent angles. And if you remember from geometry, that means our opposite sides have to be equivalent as well. And so we're going to arbitrarily set those sides equal to a 1. Okay? Now, you might remember the proportions of the sides in a 45, 45, 90, but if you don't, we can use Pythagorean theorem to figure out what our hypotenuse should be. So that's going to be the square root of 2. And so we know we have square root of 2 there if our legs are each going to be a length of 1. And so now, using the ratios that we know for our trig functions, we can find all of the different trig functions for a 45-degree angle. So if we take the sine of 45 degrees, that's going to be the opposite over the hypotenuse, which is 1 over square root of 2. But remember, we cannot keep square roots in the denominator, so we'll have to rationalize that to get square root of 2 over 2. Same thing will happen with our cosine of 45. The adjacent is also 1, and so we get the same square root of 2 over 2 answer for cosine. For tangent, if we take the opposite over the adjacent, we're going to be taking 1 over 1, so our answer will simply be 1. And then for cosecant, we're simply going to take the reciprocals of the first three. So for cosecant, we're taking the reciprocal of sine. The sine was 1 over square root of 2, so the cosecant will be square root of 2 over 1. Same with secant, take the reciprocal of cosine. And for cotangent, we can take the reciprocal of tangent, which also gives us an answer of 1. So these are what we call the special angles in trigonometry, and these are answers that you're going to become very, very familiar with over the next few lessons. We also have the 30, 60, 90 degree triangle, and if you remember, that comes from taking an equilateral triangle and cutting it in half. So if we take an equilateral triangle where all of our angles are 60, I've decided to make all of our sides 2, just to make this work a little easier. And then I cut that in half. So now I'm only interested in half of this triangle, where I have one angle of 60. I have half of another angle now, which is 30. And I also have half of the side opposite that. So now that leg is just going to be 1. So in this case, I have an hypotenuse of 2 and a leg of 1. Again, you might remember the proportions here, but if you don't, we can always go to Pythagorean theorem again and figure out the other leg, which is going to be the square root of 3. And so now we can go through the same process of finding the trig functions for an angle of 60 degrees. For the 60-degree angle, the opposite side is going to be the square root of 3 over the hypotenuse of 2. So square root of 3 over 2 is our answer. For cosine, our adjacent is going to be 1 over the hypotenuse of 2. So cosine of 60 is 1/2. For tangent, we'll have the square root of 3 over 1, so just square root of 3 for tangent. For cosecant, we're going to be taking the reciprocal of sine, but that puts a radical in our denominator, so we'll have to rationalize that to get 2 square root of 3 over 3. Same with secant, but since there are no radicals in our cosine, taking the reciprocal is not going to be an issue. We're just going to end up with 2. And then cotangent, again, take the reciprocal of tangent and rationalize to get square root of 3 over 3. Now, in a 30, 60, 90 triangle, we actually have 2 sets of trigonometric functions we can find, because we can find it for the 60-degree angle and we can find them for the 30-degree angle. So we want to go through this process one more time. For 30 degrees now, the opposite side is the 1 over the hypotenuse of 2. So the sine of 30 degrees is the 1/2. The cosine of the 30 degrees is now going to be the square root of 3 over 2. The tangent of the 30 degrees will now be the 1 over the square root of 3, which we rationalized as square root of 3 over 3. And then cosecants will be our reciprocals again. Okay, and notice here the relationship. Remember, 1/2 was what we got for sine of 60. Square root of 3 over 2 was what we got for cosine of 60. And so there's a lot of connections here. And what you come to find out with these special angles is that there really are just a limited number of actual answers that we get. And it's just about where they get assigned with each type of triangle and with each type of angle. But because there are certain patterns and there's certain answers that we get, that means that when we have to memorize these, which is what we're going to have to be doing here, you can use those characteristics to help you memorize. You can use the patterns that you see. You can use the fact that there's only certain answers. Okay? But you are going to have these memorized. You must know the 6 trig functions for the 45-degree angle, the 60-degree angle, and the 30-degree angle. You will be asked questions on parts of quizzes and tests where you are not allowed to use a calculator or where you are asked to give exact answers. So you must have these memorized. And I would highly recommend that you start now. Make yourself some flashcards, quiz each other with a friend, but do something to start memorizing these answers now. All right, so we have the special angles that you can find trig functions for, but not every angle that you are given will be a special angle. So we also need to talk a little bit about how to find the trig functions for those angles that are not 45, 60, or 30 degrees. And that's when you're going to have to use your calculator. So there's a couple of things that we want to keep in mind with the calculator. First of all, you need to make sure that you're in the correct mode for whatever you're working with. We've talked about the fact that there are 2 different kinds of angle measures, radians and degrees. So depending on what kind of angle measures you're working with, you need to make sure your calculator is in that mode. We're going to show you where to find the pi key on the Inspire, if that's the calculator you're going to be using, and you can also use the degree key. Okay, so let me just show you really quick here. We come over to our TI Inspire. Let's say I want to take the sine of 70 degrees. Okay, so first of all, I need to go to my home page. Okay, and I need to go to settings. And I want to change my document, document settings. And here I have the choice of what kind of angle I want. So if I'm looking for 70 degrees, then I need to make sure that this says degree. If I'm asking about pi over 5 radians, then I'm going to need to change this into radian mode. Okay, so it just depends on what you're working with, what you need to have for that angle. Once you do this, what I recommend is that you click on Make Default, because then it will change your calculator for good. It's not just for that one problem. It'll change it for all the problems you're going to do. So click on Make Default. It's going to ask you if you really want to do this. Yes. And then you can go back to do your work. Okay? So now your trig functions are here with this trig button. And when you click on that, you'll notice that you have the regular trig functions here, and then you have these trig functions with a little -1 exponent above it. These are called inverse trig functions. And we use inverse trig functions when we have the sign of a variable equal to something and we need to undo the sign or undo whatever the trig function is. We'll show you an example of that in just a second. But for right now, I want to take the sine of 70 degrees. And I get sine and then I get my parentheses here. And all I have to do is type in the 70 because my calculator is already in degree mode. And so when I hit enter now, it tells me it's the same as the cosine of 20. Well, that's lovely, but that doesn't really help. So what I want is the actual decimal answer. So for the decimal, I come over here and do a control enter so that I get the decimal approximation, and then I have the 0.939693 answer that I might be interested in. Okay, if I decide I want to do a radian measure, I go back to my settings, document settings, change this to radians, default just to be sure, radians, make that default. Okay, and so now if I go back to my current, where I was, now let's say I want the cosine of pi over 5. So again, I go to my trig button, I choose cosine, and now because I already have it in radian mode, I just need to do pi over 5. Easiest place to go for pi, not the only place, but the easiest place is right here beside your H button. It actually has the pi on there. If you click on that, one of your options is pi. So we're going to take pi divided by 5. And again, I just want a decimal answer for this, so I'm just going to start out with a control enter rather than giving it the chance to give me some weird answer. And so I get 0.809015 as my answer. Okay. Now, what if I'm already in radian mode, but there's just this one problem I want to do really quick as a degree? I have the option of doing that. Let's say that right now, just really quick, I want to know what the tangent of 35 degrees is. So I go to my trig, I go to my tangent, I type in the 35, but because it's in radian mode, I need to tell the calculator to do this one in degrees. And so I go to this same button where I found my pi, and if you notice right under it, there's a degree. So if I type that degree in, then I am telling the calculator to override the setting of radians and calculate this one in terms of degree. So now when I hit enter, see how it changed it to radians for me? Oh, that's all nice and sweet of them, but really, again, I just want the decimal answer, and so it's going to be a 0.700208. Okay, so that's what you need to do with your calculator to evaluate these. Now, if I'm given an application problem, in this case, I'm being given the angle. But sometimes I'm not. Sometimes I'm being given the two sides and I want to find the angle. That's when we use that inverse sign or inverse cosine, that trig function to the little -1 power. We'll see that I think in our next example. So let's keep going here. I think we'll see that in the next example. But in this example, we're told that a surveyor is standing 115 feet from the base of the Washington Monument in Washington, D.C., as you see in the picture. The surveyor measures the angle of elevation to the top of the monument as 78.3 degrees. How tall is the Washington Monument? So the first thing I want you to be clear about is the fact that we have angle of elevation and angle of depression in a lot of these problems, and I want you to be clear what that means. So when you have the ground and you look straight out, you have a line of sight that is parallel to the ground. That's just looking straight ahead. If you then look up from that line of sight, we call that an angle of elevation. If you look down from that line of sight, then that's called an angle of depression. And so in this case, as you can see, our surveyor here is on the ground looking up at the top of the Washington Monument, and so therefore it would be an angle of elevation. Okay, so as far as setting up our problem, take a look at what we know. We know this particular angle, we know this side, and we're interested in this side. So in reference to this angle, we know an adjacent side and we're interested in an opposite side. So which trig function is a ratio containing the adjacent and the opposite sides? Well, probably the best option is going to be tangent. So I want to take the tangent of the angle that I have here, the 78.3, and set it up to be equal to this opposite side of y over this adjacent side of 115. And then I solve for y. So I take the tangent of 78.3 degrees, we're going to multiply that by 115. And again, if we just come over here really quick, tangent of, oh, I didn't want to type that, let me do this. You can type it as well, but this is a little easier because then you already get your parentheses there. So 78.5. Remember, I still have this in radian mode, so I need to type my degrees for this degree problem quick. Then get outside of the parentheses and multiply by the 115. And you can see it's about 565 feet. So if we come back here, whoops, did I mess up something? Tangent of 78.3, 115. Yep, I think I just, oh, 78.3. Maybe that's the issue. Let's try that again. This time I'm just going to type it just to show you what happens. So I'm typing, and then I have to put my own parentheses in. So 78.3 degrees times our 115. There we go, 555. So that's the answer that we get. The Washington Monument is about 555 feet tall. All right, one last quick application. I know this is getting a little bit long, but I want you to be really well informed for your practice tonight. So here we have the specifications for a loading dock ramp that require a rise of 1 foot for every 3 feet of horizontal length. In the figure, find the lengths of B, C, and then the measure of our theta. So we can see that the height of our ramp here ended up being 4 feet high. That means finding B is going to be relatively easy because we're going to use this information that a rise of 1 foot has to happen for each 3 feet of horizontal length. So if this is 4 feet high, and 4 times 3 would give us 12 feet of horizontal length. So B is going to be 12. Then we can assume that the height and the horizontal would be perpendicular to each other, so this would create a right triangle, and therefore we can find C by using our Pythagorean theorem. Okay, so we're going to get C then to be about 12.65 feet. Now, in terms of our theta here, we have all 3 sides of the triangle, so we can choose whichever trig function we want. But it usually works best if we use trig functions that are more exact answers rather than rounded answers. So again, I have an opposite and an adjacent side that are exact measurements. I'm going to use those to set up a tangent function. Oh, hang on a second, we've got the wheel here. Okay, so my tangent function now is going to be the 4 over 12, which simplifies to 1/3. In order to undo the tangent so that I get the theta all by itself, this is where I have to do the inverse tangent. But again, just like any other function, I have to do that to both sides. So the inverse tangent of tangent cancels out. I just get theta. But now I have to take the inverse tangent of 1/3. So that's what these are for, when you are trying to find the theta value in a problem. So inverse tangent, 1 divided by 3 for 1/3, and then I'm going to go ahead and just do Control Enter to make sure I get a decimal answer. Now, this answer looks a little weird. Why is that? Well, it's because we're still in radian mode. And for this problem, we probably really want a degree kind of answer. So I should go back to my settings. I'm going to change this back to degree mode. Make that the default. And then go back to my current and try this one more time. So here's my inverse trig. Here's my 1 divided by 3. Take the control answer, and I get 18.4349. So I would expect that I would have an angle of about 18.43 degrees. All right, so that's a lot of information, but hopefully that's a lot of good information for you to be able to get through your practice for tonight. If you have any questions, don't hesitate to email me, and I'll try to help you out as quickly as I can. All right, we'll see you next lesson.